The Common Core standards are really big on coherence, building concepts sequentially in a manner that makes sense and building a foundation across several years. So if you look at addition, for example, the groundwork for addition started in kindergarten, and yet we've been talking in this PD module about how that whole number addition is brought to fruition here in second grade, so several years. In the same way that the groundwork for addition was laid back in kindergarten, the groundwork for multiplication is laid down in second grade. It's mentioned for the very first time in the Common Core second grade standards. So that means that you're at the forefront of building this incredibly strong foundation of sense making that will be robust enough to build for several years to build on that knowledge base and get continually more sophisticated. So we're going to talk a little bit about what that might look like, and it certainly looks like a lot more than handing students flashcards and saying we're starting multiplication, guys. So we're going to take a look at what that might entail, and of course we need to use the standard language to help frame what we do. So as we examine the wording of the standard, the first thing that jumps out to us is that children are to use addition. So addition has been that significant area of focus since kindergarten, and it should now be a strength area for your learners. So it makes sense that as children grapple with multiplication, they're actually going to be seeing it as an extension of things that they already know and they already understand, rather than having multiplication framed as, and now for something totally brand new. No, it isn't totally brand new. It naturally is an extension of what they already know, and that addition can be a really critical starting point that encourages them to begin by making sense of multiplication. You will also notice that rectangular arrays are specifically mentioned. Arrays are models that are especially useful in multiplication, and in this lesson we'll consider some of its unique advantages that lead to its getting special attention and mention by the Common Core authors. And then finally, we see that children are to write equations expressing multiplication situations as a sum of equal addends. So again, we see that their abstract representation, writing equations, is supposed to also serve as an extension of their understanding of addition and making a relationship between multiplication and addition. So we're building that connection between these two different operations. Multiplication has a variety of interpretations. For example, when we say that the distance from town A and town B is 3 times as long as the distance from town C to town D, we're using a form of multiplication called multiplicative comparison. We can also use a combination interpretation. We can think about combinations of clothes we can wear on vacation if we pack 2 different colored shirts and 3 differently colored pants. Now, neither of those 2 interpretations that I just mentioned are really evident in second grade work. Those are interpretations that they will get as they build some basic expertise. Primarily, we're going to be examining multiplication as equal groups, and then also building the connection between equal groups and rectangular arrays, since they are specifically mentioned in the standard. Because sense-making is critical to building a strong foundation for multiplication, we really need to follow the same kind of format or instructional sequence that was recommended by the Common Core authors for addition. And in fact, in the progressions document, the Common Core authors specifically mention this concrete pictorial to abstract format. So we need to follow that kind of sequencing, beginning with the concrete experiences, then using models to help students perceive relationships. That's the pictorial model. Those models that we draw help them see the relationships so that we can study them more carefully and articulate things we're noticing. And then finally, recording in more abstract symbolic formats. We'll be spending most of our time talking about the first 2 categories, although when children record situation equations for multiplication situations, then we'll shift to the abstract. The abstract requirement for second grade is to be able to write equations showing the sum of repeated addends, although some students will be ready to move into multiplication sentences as well. They still need to be able to know that how would you write that as an addition sentence. The subtitle to this lesson is Strategies, Representations, and Equations, and we're going to look at each of these categories separately, although you'll see as we go that they clearly overlap. In our discussion of strategy, I'm using the Common Core Progressions document to clarify the strategy levels that are to be developed for multiplication, and the Common Core Progressions also specifically state where second graders will likely be on that spectrum, so we'll take a look at that as well. In the first grade PD module, I went over these addition strategies that you see on the left here. I went over them in quite a bit of detail. And then in this particular PD module for second grade, we discussed them more briefly. The strategy levels for multiplication go through an analogous developmental pathway as described on page 25 of the Common Core Progressions. So level 1 is likely where your second graders will be, and there's going to be some efforts in second grade yet to prepare them for level 2. I'll talk a little bit about how that transition can start. So while your second graders are actively building level 3 strategies for addition, which we discussed earlier, they are also going to be primarily at level 1 methods for multiplication, with some groundwork being laid for level 2. Level 1, essentially, just to give you some background here about what that looks like for multiplication, it's going to be acting out problems with concrete materials or drawings and using repeated addition to solve. So visual models and or concrete materials are going to be really important learning tools at this stage. We don't begin by giving them flashcards, because that's shifting straight into the abstract without building meaning. So at this point, the primary thing they need to do is to make sense, make meaning out of multiplicative situations. The Common Core expectation then is for all of your learners to be successful at solving multiplication problems with using level 1 methods, with a shift towards level 2 when the problems involve groups of 2, because they can use skip counting for groups of 2, and skip counting by 2s should be a strength area for them. So as I said, level 2 involves skip counting, and some problems are easier to skip count by than others. Skip counting by 2s should be fairly easy, so this is something that should be actively encouraged. There is an extensive history, of course, using their doubles addition facts, and more recently in second grade with using their explorations of even numbers and how skip counting applies there. So skip counting by 2s for for multiplication problems that involve groups of 2 should not be too difficult of a stretch. One difficulty, however, that children do run into, and you need to bring this into part of the dialogue, how will we handle this situation? And that is, there will be a need to keep track of the counts. Now, if I have 3 groups of 2, I probably could just go 2, 4, 6, and in my mind, I know I've stated 3 counts of 2. But if you have 7 groups of 2, it's not so easy to know when to stop your skip count. You have to have a way of keeping track. You can't easily keep track of, I've said 7 skip counting words in my mind. That's too error prone. So what system could I use? I might use my fingers, and I know what 7 looks like on my fingers, so I could skip count by 2s until I get to the 7th finger. But I have to have some system of keeping track, and that will be one of the issues that your students will have to resolve. Now, another possible level 2 strategy that you may see students doing is very similar to skip counting, but instead of sounding like 2, 4, 6, 8, it's additive counting, where you keep a running total. So you might actually say, well, let's see, 3 4s. 4 plus 4 is 8, and then one more 4 would make 12. That sounds a little different than going 4, 8, 12. So additive counting is another method you might see here. Here you see some images of curriculum that's actively attempting to support a shift towards level 2 methods. Now, just completing these activities will not make the idea apparent. Classroom dialogues, which you listen at, what did you notice? How did you figure this out? How did that help you? Why can we do that? Why does that work? These are really helpful types of dialogues to have to ease the transition by which students see how skip counting can play a role in solving multiplication problems. Excuse me. Level 3 methods are not really expected of second grade children in the Common Core. The Common Core states the expectation that all children will have by the end of the year, but certainly you will likely have some children who are ready for level 3 and who might actually be starting to use them. So for that reason, I'm showing you a couple of things you might notice. I've certainly met a number of second graders who are ready to make this transition. And just to give you an example, my oldest daughter actually developed the first method entirely on her own with no instructional attempt to foster it. And that's the ×4 facts are really like doubling twice. Her teacher and I discovered that neither one of us had taught her, but it was clear from our discussion with her that she completely understood why it worked and was actually a little surprised that we would even ask questions about something that seemed so obvious to her. So you do run into children who can come up with some of these methods on their own. The other reason that I show you these methods is so that you have an idea of where your students are headed and you recognize how important it is for them to have foundational understandings. The methods that are here do not make sense to people who don't understand multiplication. The reason why the double twice method made sense to my oldest daughter was because she completely understood that if I have 2 groups of 3 and then another 2 groups of 3, that's 4 groups of 3, so all you have to do is double it once and double it twice. She understood that concept, so she was able to construct this strategy. So building that foundation is really important. So if children are going to build that strong foundation, what are some models or representations that lend themselves towards sense making and also really towards beginning to think through some of the types of strategies that might be available to us? So clearly strategies and representations have a relationship with one another. In the 1990s, 2 researchers, Kuba and Franklin, researched children's early experiences with multiplication, and they found that children greatly benefited by making sense of multiplication using different representations where they actively explained and thought about how the representations were connected or related to one another. So instead of just using one representation, the children who were exposed to more than one way to represent something and who could easily talk about how these representations were similar and different and how they illustrated similar relationships, those students had deeper understanding. So we're going to take a quick look at the most commonly used representations for multiplication, exploring some of the advantages and disadvantages. And please keep in mind that the goal is not to choose which one you like and stick with it, but rather to help students see these different representations and to make connections between the multiple representations. The set model involves making, by the way, I just need to say one thing. We do not use the terms set model and measurement model with students. And typically we can use the word array to refer to rows and columns. You'll see that in a minute. But the goal isn't to give them the jargon, it's to give them the tools. So set model is really just a teacher term. Okay? And the set model involves making groups with equal amounts in each group. So when I am telling a multiplication story about bags of cookies where each bag has 3 cookies in it, that's actually a word problem that elicits the set model as the basis of the problem. And children might easily solve it by drawing circles on their paper to represent the bags and then drawing inside it the numeral 3 or 3 items representing the cookies inside each circle. The set model works really well for children in the early stages because it's very easy to model. And of course, level 1 methods are where they're kind of acting it out or modeling the problem using visual representations often or concrete materials. So children's first exposure to multiplication almost always uses the set model for this reason. The downside is that it doesn't lend itself well to the properties of multiplication. So I think that when you are just getting started with multiplication, use some things that really help build the set model to begin to build that foundation. Eventually, you're going to want to fold in some other representations as well and have them make connections between those multiple representations. Now, I said it's not really very good for helping students see the properties of multiplication. What did I mean by that? Well, let's take a look at the image here to demonstrate. What you see are 3 bags of pears with 6 pears in each bag. Now, especially if I love pears, There is no way that I think that 3 bags of pears with 6 pears in each bag is the same as 6 bags with 3 pears, because I'm thinking about which bag of pears I get, and 6 pears is different than 3 pears. So the commutative property is really not very evident, because to me these situations seem entirely different. They're not the same. So a teacher who says that 3 times 6 is the same as 6 times 3, that's not intuitive to me if my mind is stuck in this set model. And so there's a real danger that I just stop making sense because it doesn't make sense, and just say, well, the teacher says this, so I guess it must be true. Now we're going to come back to this idea in a minute with a model that better facilitates that aha. The measurement model uses length as a tool for making sense of multiplication, and this can be done by modeling on a number line using the number of groups as the number of jumps, and then the step size of each jump as the number within a group. And a tape diagram can also be used to model multiplication, and that model plays into some really useful and advanced problem-solving strategies as children progress in multiplication and as the problems get more difficult. So that tape model is also very, very helpful and would be an example of this measurement model that kind of uses the idea of length as a model for it. The measurement model supports the connection to skip counting. It also allows children to see the meaning of multiplication in a context that can also deepen their expertise and understanding of our number system. And as you might expect, and as I just mentioned, it also plays into children's development of linear measurement, since all measurement is essentially repeating the same size of unit over and over. Okay, now we arrive at the rectangular array, which was specifically mentioned in the standard. And you see here a dot array and a grid array, and these are both useful tools. Building familiarity with this tool now will also bear fruit later in 3rd grade and beyond, when children begin to work more formally with area. But for now, we're going to use it to make sense of multiplication. This model also has some distinct advantages because it allows children to see those properties of multiplication that were not so obvious with the set model. So the commutative property is not obvious in the set model and not so obvious in the measurement model, but you can get students to notice that you get the same total. However, even if you get them to notice that you arrive at the same total, there's no way of determining whether that's happenstance or arbitrary or just good luck, or why is that always true. So I can use the pair model to find out that 3 groups of 6 is 18 pairs and that 6 groups of 3 is 18 pairs. But the set model doesn't really imply to me why that would have to be true, that would always be the case. But with a rectangular array, you can get that aha because the array can be examined from different perspectives, and it can be simultaneously seen as 3 rows of 6 and as 6 columns of 3, depending on how you look at it. Therefore, these two situations must result in the same total because it's the exact same array. For this reason, children's work with multiplication needs to lead them eventually to arrays, and they should have opportunities to ponder this intriguing aspect of arrays. Here in this slide, you actually see several images from curriculum that build on an array idea. The stamps on the bottom are things that tend to come in arrays. We might not think about it. The cupcakes were more putting them in rows than for groups. Both of those came with word problems associated that I don't have here. And then the image off to the left is a kind of an unusual one. It's intersecting lines. So if you have one line intersecting with one line, you only have one intersection point, 1 point of intersection, so 1 times 1 is 1. If you have 2 lines crossing one line, 2 intersection points, 2 times 1 is 1. So here you see that as an idea, and again you can look at it from more than one orientation. Okay, now we're going to take a look at the transition to writing equations. The Common Core requires all 2nd graders to be able to write multiplication equations for arrays using addition. So we're going to take it a bit further in this presentation because some of your learners will be ready to go further, but it's important to know that the ultimate goal in 2nd grade isn't being able to do multiplication sentences, it's being able to do the addition. So instead of thinking of children who can write the multiplication sentences as reaching the end goal, they also have to know what it looks like for an addition. So you might have them do it both ways if you think they're ready for the multiplication sentence. For students who might not be ready yet for that symbol, they should stick with the addition. Before we discuss multiplication equations, it's important to recognize a fundamental way in which addition equations differ from multiplication equations. In addition, each of the numbers stands for a similar thing. We don't add planets and bugs because our sum would not make any sense at all. There's nothing that planets and bugs appear to have in common that we could then be adding. We can add toy dolls and toy trucks because they have an intrinsic similarity that we can label as toy. So when we get a sum, the sum means something. It means the number of toys. In multiplication, it is no longer true that each of the numbers stands for the same or similar kind of thing. So each of the numbers has a distinctive meaning. The multiplication sign, which we sometimes read as times, can also be read as groups of. So this equation could be read in words as 3 groups of 4 is 12. Notice that the 3 is actually referring to the number of groups. The 4 is representing to the number inside each group, and the 12 refers to the total number. Students who make sense of multiplication, they know this. They do not think that 4 times 3 is exactly the same as 3 times 4. They know that it results in the same product, but they know that 4 groups of 3 is the same total as 3 groups of 4. They don't just think, oh, numbers don't matter, you can switch them whenever. Okay, 4 groups of 3 would be 4 times 3. 3 groups of 4 would be 3 times 4. So they have a sense of what it's meaning. As you build a bridge to equations, it's important to remember that the standard specifies rectangular arrays, and these serve as wonderful starting points for writing equations. And doing so can foster important connections. Children can connect skip counting, addition, and multiplication, and can even use the array to recognize equivalent equations, which can lead them to an aha about the commutative property. Here I show an example of how that can play out by having children share different ways they count the squares in this array using skip counting. One person counted by 3s 4 times, so we can ask them how we could write that as an addition equation. Another individual might skip count by 4s 3 times, so we could write that down as well. And then we could comment on how there were 2 ways of counting the exact same model, so these 2 sentences must be equivalent. Once you show that it's an equivalence, you might then convert it to a multiplication sentence to show 3 times 4 is the same as 4 times 3. And ask them what they notice. That 3 groups of 4 results in the same total as 4 groups of 3. And that could be to their advantage to think about that relationship. Probably strategically that will be more at their advantage in 3rd grade. I want to just go back for a minute and tell you the story about when I found out my daughter knew this times 4 trick. She also showed commutative property because she had 9 times 4, 9 groups of 4 was the essential problem. And she actually solved for 4 groups of 9. So that's how I discovered she was using this strategy, and I asked her why she did it, and she said, well, because 4 groups of 9 are easier to figure out than 9 groups of 4, and it's the same thing. So, so that's an interesting relationship to figure out. These types of rich dialogues in which you elicit these relationships and connections and ahas build children's capacity to reason abstractly as they search for patterns that shed light on the way our number system and operations function. And as such, they inherently engage children in the standards of mathematical practice. As you lead dialogues, eliciting student strategies, choosing representations, and fostering a transition to writing equations, keep in mind that Kuba and Franklin research that I mentioned earlier, making connections between the concrete representations in the arrays, between arrays and equations, between skip counting and addition equations, and between addition equations and multiplication